Hello, good evening. So let us start the session. Okay, so in last session we discussed about efficiency and losses of transformers. So uh, we would continue from where we left in the last session.
Okay, sir.
Okay, great. I hope my screen is visible.
Yes, sir.
Great, thanks. Yeah, so this was the problem where we left, and I asked that you try it on your own and let me know. So I hope you must have tried.
Uh,
So, Adil, did you get the answer for this?
sir,
Yeah, yeah.
sir, actually, we are now going in week 4.
Week four, yeah. So, week four is about auto transformer, right?
Yeah. Octo
Yes.
transformer.
Yeah. So, let me finish this last problem of week three, and we will enter into auto transformer. Is that okay?
Okay.
Okay. So, you tried this problem last week, or in the last week's assignment, there must be some problem related to this problem, right?
Yes, sir. I got it wrong.
Oh, you got it wrong. Why?
Because short circuit test performed from HV side, no? It was not
Yes.
rated current.
It is not rated. Yeah, that's the point you had to
Yes.
catch.
Yes, that
So,
I missed that point. Made a
y-
mistake by taking it as a rated current. I didn't notice
oh,
that.
and you must have put the rated loss as 9.45 copper loss, right?
Yes, I
And
took
that's why
the
you,
full load copper loss. Full load copper loss as 9.45 kilowatt. But that's not
yeah,
true. Sir,
yeah,
please
it should
explain
be
how to
high.
do.
Yeah, yeah. So let me explain this problem. See, first thing is that you should know that OC test is performed on LV side. So whatever power is given here, that must be core loss. I hope it is fine. Now, the thing with copper loss. So first you should identify from the circuit parameters whether the machine is operating at a rated load or not. So let us calculate the rated current first. So we can compute it from 600 kVA divided by how much? How much here it should be? Since the SC test is performed on HV side. So we will take HV side voltage, right?
Okay.
So here it should come out to be 18.18 amps. So clearly we can see that AC test parameters are at 10 ampere, which is less than the rated current, 18.18 ampere. So whatever the losses is given, 9.45 kilowatts, it is corresponding to 10 ampere, right? Which means there must have been some I square R. So I square R, and I here must have been taken as 10 amps, and whatever R should be. So this power is directly proportional to I square, right? So 9.45 divided by 10 square is equal to whatever power copper loss at rated condition should be divided by 18.18 square, right? So from this expression, you would be able to compute copper loss at rated condition. Okay. So if you
Okay.
compute this, you will get 31.239 kilowatt. So this is the rated copper loss. Now you can compute efficiency at the full load. So efficiency at full load is equal to, first, what is the output power? That is the rated, which is 600 kVA into 0.75 power factor. So kVA is 600 kVA, right? So into 0.75 power factor divided by output plus losses. So let me write first the output plus core loss. We can directly conclude it from the OC test, that is 9 kilowatt. Plus copper loss we computed just now at the rated condition 31.239 kilowatt. So if you compute this efficiency, you will get 91.8%. So this is how we can compute. First, we need to verify whether the parameters of the short circuit test are at the rated condition or not. If not, then we have to scale it at the rated condition, and then we can plug in at the place of copper loss. Then only you will get the correct solution, right? So this kind of mistake, I hope you should avoid in final exam, okay? So that's all about the topic from efficiency and losses. If any final question is there, I would be happy to take it. Otherwise, we will move to our auto transformer topic. Is it fine? Deepak, have you joined this meeting? Okay, so let us go ahead. So I hope you are able to see this question, and there is one mistake here. This is not auto transformer, this is transformer. Okay, this question is based on voltage regulation concepts. So first read the question carefully, and then we will solve it step by step. Okay, so I hope you must have read this problem. Here, 240 by 200 volt single phase transformer is given, and low voltage side is sorted, and HV side is connected to 5 volt. Okay, now it draws 14 ampere current from the supply at 0.3 power factor. Okay, so after observing this data, 5 volt, 14 ampere, 0.3 power factor, you must first compute the power. What is the rating of the transformer, okay, at this condition? Now, the next condition, it is stating that suppose the HV side is fed from an alternating supply so that no load LV voltage is 200 volt. Okay. So, and further it is saying estimate the LV side voltage drop that would occur if a load draws 40 ampere current at unity power factor from the LV side. Okay. So we will move step by step. First thing is we need to identify the circuit parameters, resistances and reactances. So for that, uh, we must know certain things. If LV side is sorted, it means it is talking about SC test. Okay, you can infer from this statement that it is talking about a short circuit test. Now at the short circuit test, how did we compute the circuit parameters? So we have HV side voltage, we have HV side current, we have HV side power factor. So we can compute first thing is power. 5 into 14 into 0.3. Just VI cos phi, right? Now it will come out to be how much? Let me compute. Into 5 into 0.3. It is 21 watt. Okay. Power we have computed, and whatever power at this rating we are getting here, that should be equal to I square R losses, right? So here resistance we can compute RSC is equal to 21 by I square. Okay, so this will be 21 divided by 14 square. It is 0.1 ohm. Are you getting it till now?
Yes, sir.
Great. So RSC we have computed. Now next is the short circuit reactance XSC. Okay. So in short circuit test, what we did, first we computed impedance, that is V by I, 5 by 14. Okay. So it will be 5 by 14. It will be 0.357 ohm. Now XSC we can compute ZSC square minus RSC square. Okay, so it is 0.34. Okay, so we have computed short circuit parameters, right? Now we need to compute LV side voltage drop that would occur if load draws 40 ampere current at unity power factor. Okay, so all these parameters we computed from HV side, right? Because LV side was sorted and HV side parameters were given for short circuit test. So we all computed these parameters from HV side. Now we want to compute LV side drop. So first what we'll do, we will compute HV side voltage drop and then we will refer it to LV side. Okay, is that making sense? Adil, is it correct?
Yes, sir.
Okay. So first we compute voltage drop, which is nothing but IR cos phi plus Ix sin phi, right? This expression you might have seen from voltage regulation expression. Now plus is when lagging and minus is when leading. So here it is given unity power factor, so we can take plus case. Okay, so let me write current is 40 ampere, right? 40 ampere into RSC. RSC we have computed 0.1 into cos phi, which will be again 1, plus ix, ih 40 again, x we have computed 0.34 into sin phi. So if cos phi is 1, it means sin phi is 0, right? So we will get 4 volt. 4 volt on HV side. This is the 4 volt of drop occurs at HV side. Now we need to compute drop from the LV side. So let me transform it. 4 into the ratio is given 240 divided by 200. So 4 into 200 divided by 240. So it should be 800 divided by 240. So 3.34. Is that correct? Is that correct?
Yes, sir.
Okay, so if it is correct, then I guess you all missed one very important point and you got confused in LV and HV side parameters. So read the last statement where it is highlighted in the question. Can you point out any mistake done in the solution?
Sir, we have used the current on the low voltage side and resistance and reactance value of the high voltage side.
Perfect. That is the mistake that is done. So here either we should have first transformed this 40 ampere to HV side, or we could have transformed resistance and reactances to the HV side. Okay, then we could have transformed to LV side. So here one factor which is 40 volt we directly used from the HV side, which is given for the LV side. So first 40 amperes should have been transformed to HV side, and that could be done by taking this ratio 200 divided by 240. Then whatever value it will come, that would be the voltage drop at HV side. Now again we had to take this ratio, this transformation, to identify the drop on the LV side. Okay, so I hope everybody got what mistake we did. So let me just take the ratio 200 divided by 240. So it is 3.33 volt.
Sir,
So yeah, go ahead.
as per the formula for regulation, it is V minus V1 minus V2 dash equal to IR cos phi plus or minus IX sin phi. Then
Yes.
how you wrote V minus V equal to, then how you wrote it V equal to IR cos phi plus or minus IX sin phi?
Yeah, this is not voltage, this is drop. This is drop we are calculating. And drop is not V1 minus V2, it is V2 minus V2 dash, no load voltage
Yes.
minus full load voltage. Okay, it is
Okay,
not
it is
primary minus secondary. Yeah.
okay, it is the difference between those two voltages, no?
Yes, yes, yes.
Okay, okay.
Since in the question we are asked to compute LV side voltage drop, so we are concerned related to drop only. Okay.
Okay, okay, okay.
Yeah, so this is 3.33 voltage we have computed, and now at the place of 4, if you write 3.33, then you will get how much? It will be 2.77 volt, 2.77. So this will be your final answer. Okay. Any final doubt in this part? If not, then other condition here in the next part of this problem. Now the HV side is fed from the AC supply, okay? So that no load voltage, no load LV side voltage is 200 volt, which is as it is, okay? Now again we have to estimate the LV side voltage drop that would occur if load draws 30 ampere current at 0.6 lagging power factor from LV side, okay? So I think you can compute it very easily as you must have observed the previous part. So please go ahead and solve it. Okay. And tell me the answer. It is just one line solution. Okay. You can easily find out the answer. Is anyone trying the problem?
Yes, sir, what is R?
R is 0.1 ohm. Okay. So again, the current is given from the LV side. So first we need to compute the
6.9.
6.9 volt of drop from LV side, right?
Yes, sir.
Okay, we will see. So IHV is 30 into 200 divided by 240. It's 30 into 200 by 240. It is 25 amps. Now, drop is equal to IHV into RHV plus ILV into XLV cos phi to sin phi. Okay, so IHV is 25, R is 0.1, cos phi is given 0.6, right? And I am using here plus sign because lagging power factor is given. For leading, you could have seen the derivation from the lecture, or you could derive on yourself. It will come out to be negative. And sorry, why I wrote IL, it is IHV. So 25 into X is 0.34 into sin phi will be 0.8. So if you compute it, one 1.5 plus 6.8 and 8.3. 8.3 volt of drop occurs at the HV side. Now drop at the LV side, you just have to transform 8.3 into 200 by 240. So yeah, it is 6.916 volt. So it is correct, 6.9 volt, 6.91 volt to be precise, you will get. So this was just one step calculation you could have done easily. Okay, any doubt in this? Okay. If no doubt, then we will move ahead to the auto transformer topic.
Hello.
Yeah, Deepak, go ahead.
Sir, please explain little bit about voltage regulation formula.
You want derivation of that?
No, suggest you have give some concept of this, sir, because I did not attend the lecture, sir.
Okay, so basically voltage regulation is what? It is the drop from no load voltage to full load voltage. Okay, so let me explain that a bit for you. Just wait a second. So see, yeah. So there is some load. Let us represent as resistance and reactance. Let us suppose this is secondary side of the transformer. And this is primary side of transformer. So we have transformed all the equivalent circuit parameters on the secondary side so that we can include them with the load. Okay, so whatever the voltage that you will see here, E2, let us call them E2 since it is secondary side. And this is the voltage V2. Okay, so if the circuit is, or the machine or transformer is operating at no load, it means this current I2 will be 0. Okay, so whatever E2, that will be reflected to V2. So V2 is equal to E2, we can say, right, at no load.
Yes, sir.
Now, let us suppose some load current is flowing. Okay, I2, some load current is flowing. So what will happen to the V2 value? So if you apply this KVL in this
Sir,
case,
it will decrease.
it will decrease, and the exact value should be E2 plus I2 R2. Let us talk in this sense. I2 Z2. Okay, or both combined.
Sir, it should
Now,
be minus the
V2 is equal to E2 plus I2 Z2. एक second, I2. Yeah, E2 minus E2 plus I2 Z2 plus V2. Okay, so if this condition you are getting, then E2 minus V2, our agenda is to compute the difference between the no load voltage and full load voltage. That should be I2 Z2, right? So if we are assuming this, or not assume, Z2 will have some R plus Jx, right? So if you break it, you will get in terms of V. Let us suppose this is the voltage and this is current lagging. This is voltage, this is current lagging, and this is power factor angle. So it means I2 has some angle lagging to the voltage. So whatever R will be here, R will be in phasor of I. So the drop will be in line with I. So R2, I2, R2 cos phi 2. And whatever the reactive drop, that will be orthogonal to that drop. So I2 x2 sin phi. We can write in that manner. Do you agree with that?
yes, sir. But sir, R2 should be in V direction, right?
R2 should, yeah, means if you are using cos phi 2, this phasor will be shifted here. And if you are using sin phi 2, then this vector will be shifted here. If you remove this sin phi and cos phi, then I2, R2 in the same direction. Do you agree?
Okay.
See, resistive drop is generally occurs in the same direction of the current, right?
Yes, sir.
Tala
But sir,
kam
we
hai
will add on V vector.
Yeah, when you need to shift this vector in align to V, if you want to align this vector in the direction of V, so I2 R2 cos phi 2 you have to use. And
Yes,
if you
sir.
want, if you, and if you align to I2 x2 in V direction, then you need to use, let me use different color, I2 x2 sin phi. Do you agree with it?
Yes, sir.
Yeah. So all those things which we have indicated in phasor, if you want to write in the direction of E2 and V2, so you have to write I2 R2 cos phi 2 plus x2 sin phi 2. Okay. When this phi is lagging, when this phi will lead, then what will happen? Let us suppose this is the I when this angle is leading. Okay. So if it will lead again, I2 R2 will align in the same direction with cos phi 2. But when you take orthogonal, so this will be the direction of I2 H2. Okay. And if you multiply with sine phi 2, this will be 90 minus phi. So if you multiply or if you break that component along V, it will be opposite to the direction of V. Hence, that vector you can write it as cos phi 2 minus x2 sine phi 2. When current was leading. First case was for lagging. Did you get it?
Yes, sir.
Yeah, so this is all about voltage regulation, why this negative sign arrives when the current leads and why this positive sign when current lags. So this drop is overall drop uh, that occurs from the no load to full load transition. Okay. And now if you go one step further, there will be a frequently asked question that what is the maximum voltage regulation that occurs, right? Someone was asking in
Yes,
between.
sir.
I didn't get their question. So if you want to ask now, ask. I will move towards maximum voltage regulation or zero voltage regulation. Any doubt in first part, in phasor or this expression? Any doubt there?
No, sir.
Okay. So maximum voltage regulation we have to find out. So generally we differentiate voltage regulation with power factor angle, right? So at what power factor or what value of resistance and reactance this maximum voltage regulation occurs. So you just need to equate it to zero, right? Maximum minima, I hope you might have studied. So uh, when the maxima occurs at some point, it means differentiation or slope of that point should be zero, right? So we are doing exactly same thing. So let us take this first case for lagging power factor I2 R2 cos phi 2 plus I2 H2 sin phi 2, and you differentiate it with d phi 2 is equal to 0 or d phi. Okay. So if you differentiate it, what will you get? Deepak,
Sir.
after differentiating, what will you get? You just need to differentiate this term.
No, sir. I2
Uh,
R2 minus
mi
cos phi
minus
2.
sin phi 2.
Yes, sir.
Differentiation
Minus
of
sin
cos
phi
phi
2.
is minus sin and plus
Yes, sir.
I2
Yes.
H2 cos phi 2.
Cos phi 2.
Yeah. And we have equated them to 0. Now, if you take this component on the left hand side and take only sin phi 2, I2 R2 sin phi 2 is equal to I2 H2 cos phi 2. Okay. Now you will get a condition sin phi 2 and bring cos phi 2 on the left hand side and divide. You will get tan phi 2
Equal to x2 by R2.
H2 by R2. That's it. So this is the condition of your maximum voltage regulation. And since we started with positive sign, it means maximum voltage regulation will occur at the lagging power factor. Okay. It can never occur at leading power factor. So if you, after, drawing the curve, the voltage regulation curve with power factor angle, if you draw, you will get such type of curve. Okay. So this curve, this is the angle tan phi 2, which is tan inverse H2 by R2. And if you extend this curve, it will be like here the zero voltage regulation will occur. Okay. And this point also we will compute. That will be the condition of zero voltage regulation. So this condition this condition is maximum voltage regulation, and this condition is zero voltage regulation. Any doubt in maximum voltage regulation?
No, sir.
No. Okay. So I hope you can easily derive the condition for zero voltage regulation. But since we are discussing, just finish with it. So what should be the zero voltage regulation condition? You just need to, again, V2 minus V2, you have to equate it to zero, which is I2 R2 cos phi 2 plus, let us assume we are taking lagging power factor condition with positive sign, I2 S2 sin phi 2. And with positive sign, if negative angle will appear, it means it should be leading power factor. Or if the tan phi or cos phi or whatever that angle will come as positive, it means our lagging power factor assumption is correct, right? So we just have to equate it to zero. This time we do not need to differentiate because zero voltage regulation is a straightforward. You just need to equate to zero the value of voltage regulation. So minus sine phi 2 divided by cos phi 2 is equal to R2 by X2. Can I write like this? Tan phi 2
Yes,
is
sir.
equal to minus R2 by X2. So this tan phi or this power factor angle is coming as negative. It means the power factor should have been leading. So if leading, then phi 2 should be tan inverse R2 by X2. And that's what I have drawn on the graph. So this is the point which is negative on the power factor, and this value is tan inverse R2 by S2. So I hope concept of voltage regulation is clear to you guys. If any doubt is there, you can still ask.
Sir, for the first case, we have concluded that maximum regulation will occur only when power factor angle is positive.
Yes, for lagging power factor. Yeah.
Okay, sir.
See, we moved
Sir,
ahead.
only,
Huh, go ahead.
sir, I think, but sir, sir have derived another formula for that in terms of divided V1.
Okay, so yeah, that is percentage voltage regulation. If you do it here, sorry, V2. If you divide by V2, V2 minus V2 by V2, that is the precise formula of voltage regulation, right? So if you divide it by V2, then you will get the percentage voltage regulation. So if anywhere you will be asked in terms of percentage, you divide it by V2, right? So you will get a percentage, and this term E2 minus V2 is dropped. So this is exact value will come in terms of volt. And anyway, if you
Sir,
carry,
in terms of percentage.
so in percentage, you just divide it with V2. Or anyway, if you carry V2 in all those expressions, you will get the same expression. But that is for percentage voltage regulation, not for exact. Okay. And sometimes you might observe that at the place of V2, E2 is written. Okay, so some book consider V2 as E2, or some book consider it as V2. But generally, if it is asked in exam and you are confused, you just go ahead with V2, because V2 is mostly in many gate exams, and they consider as V2.
Yes, sir, sure, sir. We will go for this.
Okay. So the question, I think someone has asked that why did we call maximum voltage regulation appears at lagging power factor. So the reason being, we assumed initially that it occurs at lagging power factor. Hence, we moved ahead with this positive sign. Okay, and at the end we got positive value of tan phi 2. It means our assumption was correct, and it will appear at positive value or lagging power factor. On the other hand, in zero voltage regulation, we moved ahead with assumption of lagging power factor, but at the end we got here negative sign. It means our assumption was not correct, and zero voltage regulation should occur at leading power factor at a negative power factor angle. Okay, Neeraj, was it your question?
Yes, sir.
Did you get it? Any doubt?
Sir, I will read it afterwards. Sir, please continue ahead.
Okay, great. You just revisit and let me know in the next session if you have doubt. So that was the voltage regulation concept. Yeah. So we are entering into auto transformer. Okay. So this is the problem. I hope you are able to see. So indirectly, we have to compute the efficiency of auto transformer at the rated load, right? So, okay, let me draw a auto transformer. So here 1500 volt. So what voltage can you observe at the secondary terminal?
So 1650 volt.
1650 volt, and that is what written in the problem as well, right? When this 1500 divided by 150 volt of two winding transformer is used as an auto transformer, so essentially this was the two winding transformer 1500. Here 150 volt. Ideally here it should be 150 or 1500. If current is entering this dot, it should leave this dot, right? So this should be the direction of current. So the same direction of current we will use here in the auto transformer, I1, I2. Am I right?
Yes, sir.
Yeah.
Sir, how can we decide the direction of current I1?
So see here 1500 volt winding transformer, if we have decided as this dotted, it is entering one dot. So generally in two winding transformer, what happens? If load is connected on the secondary side, the current enters on the first dot and leaves the other dot, right?
Yes, sir.
Yeah. So similarly, this suppose this winding we are directly replacing here, and just this winding is relocated here. So it should leave this polarity, this dot polarity. if nothing is given, you have to assume it as additive polarity, right? So that both voltages should get added. Otherwise, if subtractive polarity would have been given, we would have reversed it and we would have reduced 1500 minus 150. But if nothing is
Okay.
mentioned, you have to assume that both voltages are getting added. That is the basically use of auto transformer. We just increase the rating of auto transformer so that we can
Okay.
maximize the efficiency and increase the power rating of the transformer. So that we will see what values should come in the next part of this same problem.
Okay. Let's suppose, sir, we have connected the 1500 volt at right hand side. Means this
Mhm.
side, opposite side. Then what
This side.
will be the direction of S, sir?
Okay. So
Then what
even
will
if
be the
you
direction of I1?
I1, so see, let us suppose you have connected. You are saying this 1500 volt.
Yes, sir. We have connected this side.
Okay, and 150 is same.
Okay, that
Is
is
this?
same. All other is
Uh,
same, yes, sir.
yes, yes. So whatever possibility you must try to draw on yourself and see what other possibilities should come. Actually, there are 2, 3 possibilities that might come, but in terms of subtractive and additive only. Okay, it will not come like something else. So, but you must try on yourself. And what are the
Okay, sir.
advantages of additive polarity and what are the drawbacks of subtractive polarity? So that you must analyze.
Sir, in additive polarity, we got additive voltage means we have added the whatever voltage we are applying or whatever inducing the in the coil, we are adding that voltage, so we can transfer more power, you can say.
Yes, yes, exactly. That is the reason. So let us see here. Let us assume I2 is equal to 10 ampere. Okay. So in two winding transformer, what will be the output power if load is connected across the 150 volt? If load is connected across 150 volt, the power should be, or kVA should be
15
rather,
k.
15
1500
kg.
VA. Okay. And
Yes.
at the same time, if you compute here, if you have connected a load and same current is flowing, I2 is equal to 10 ampere, then your kVA rating would be 16.5 kVA, right? So it is way more than like 11 times of whatever kVA of two winding transformer. So kVA of auto will be 11 times of kVA rating of two winding transformer. Okay, so you can see with this connection, you are gaining in terms of kVA rating and power rating of the transformer. But again, you are losing in terms of insulation. Your two windings are
Yes, sir.
now not insulated with one another. If some fault occurs at any side, your both winding will get reflected because of that. So you are losing in terms of
Yes, sir.
insulation, but you are gaining in terms of power.
Yes, sir, in auto transformer.
Yeah, in auto transformer.
Okay, sir. Okay.
Okay, so let us go ahead with the problem. So first thing is to compute total load power when auto transformer feeds a unity power factor load with the rated voltage at its full capacity. Okay, so
So
yeah,
165 kVA.
165 kVA. I guess it is the correct answer, but let us go step by step. I will write your answer. 165 kVA. So, yeah, first we need to compute I1.
Sir, I
We do not
think
need.
this problem we have solved, sir.
Okay, solved when? Where?
Sir,
Sir,
yesterday's session.
yesterday session.
Okay, in
Sir,
yesterday's session, I think. Okay.
but
So should I
the
skip this part?
second part, sir, second part was not there, sir. The original two winding
Oh,
transformer had 96%. In this part was not there. In
okay, okay. So just let me take 2 minutes and solve first three part quickly, and then we can shift to the second part. So because both will be related to each other.
okay,
So
sir.
I1 just quickly I will compute 15 kVA divided by 1500 volt. So it will be 10 amps. Similarly, I2 15 kVA divided by 150 volt. So it should be 100 ampere, right? So I2 is 100, I1 is 10 amps. So our output power is 1650 volt into 100 amps. So it will be 165 kV. Okay, so let us jump to the final part. So two winding transformer has efficiency of 96% and 0.9 power factor. So if you are shifting from two winding transformer to auto transformer and all the current ratings and voltage ratings are same or equal, it means losses are same. Losses must be equal for both the windings, because see, in this winding also same current is flowing, in this winding also same current is flowing, and there are two windings only, and losses will occur in the winding resistances. Okay, so
And sir,
whatever
core.
loss, core, yeah, core, core are same, right? See, whatever
But sir, we are
the,
reducing core right here.
but that is not provided in question. If that will be provided in the problem explicitly, that core volume or core area is reduced, then you must consider that condition. Yeah, indirectly you are correct, because core structure of both the transformer will change. But for problem solving purpose, whenever such information is not provided in the problem, then you must have to assume that core losses are same, since frequency are same, right? Generally, even frequency information is not given in this problem. So what will you do? You have to consider same core loss. There are no other way.
Yes, sir. Yes, sir. But sir, they have not given any core loss or copper loss, right?
Yeah, because see, for such type of problem solving, generally throughout all the problems, whenever you see, you will not see that core loss is getting vary. So we generally go ahead with on. We are only concerned with copper losses, and in most of the case, we have to take losses equal, because windings are same, resistance winding resistances are same, so losses also we consider equal. If you would be provided with some parameters where frequency or core area is provided, then you can go ahead with, change in core area will be reflected into core loss. So in that case, you can compute. Yeah, Neeraj, go ahead. You have raised your hand.
Sir, the core losses are dependent on the flux density, sir. And flux
Flux density
density
and frequency. Yeah.
and sir, flux density is determined by the voltage applied. Sir, here on the secondary side, the voltage is getting increased, sir, 1650 volt. Sir, will
Yes,
this
yes.
affect the core loss or not?
That is very good question. So, yeah, you see here voltage values has been increased from 1500 to 1650. That it means you are saying that if voltage is increased and frequency is constant, then your flux density should get increased, right?
Yes,
But
sir.
again, here frequency information is not provided. Had it been provided, we could have derived. Or let us suppose uh, you are assuming that 50 hertz of frequency is there. Okay, generally for this transformer 50 hertz of frequency we assume. So in that case, yeah, your core loss should come in the picture, because your B max is nothing but directly proportional to V by F. So since your V is varying from 1500 to 1650, yeah, your core loss should increase ideally. But again, the limitation is with the question and parameters and examiner. They generally are not concerned with core loss in such type of problems. But that must increase because, and even ideally, if you see the size of auto transformer, it also reduced significantly compared to two winding transformer. So even your area is also getting reduced. So if you see uh, AD current losses, so it is KE V square, sorry, BM square
Yes, sir, only V square because Vm is
TS
directly
thickness.
proportional to F V by F.
Yeah. So generally it depends on V by F square, and so they must provide some area or frequency information, but they generally avoid it to make such problem very simple. But in ideal scenario, definitely core loss will also increase.
No, sir,
So I
but
would,
we are reducing the area of core, so that will decrease as well.
if area of core you are reducing and your Bmax is increasing, it means your core loss will further increase, isn't it?
But sir, core losses depend on the material. Means, if we reduce the material, core loss should reduce, na?
Yeah, if okay, in that term you are saying, yeah. In that term, yeah, it should reduce, but that will be again very detailed analysis will be required because if you are reducing the material, okay, so let us suppose you have what happened? Yeah, you have this much of material. Ideally, generally, we are speaking this much of material. Now you have reduced the material to a smaller portion. Now, whatever, and one more thing, you are increasing voltage here. Let us suppose 1650 volt and here 1500 volt. Okay, first thing, voltage is increasing, so one factor for core loss is increased. Another thing is you have reduced the area. So if area or volume of the material will reduce, then yeah, iron loss will reduce. That is true. Here, iron loss will increase. But another factor you are missing out here, your flux density because of 1650 and a smaller section of area, your flux density, let me, maximum flux density in this portion will be highly dense compared to this portion. Not just because of this voltage we have considered, but other factor is you have a smaller portion and you have even higher flux, then your this material will be highly saturated, and as you enter into saturation region, even very small amount of voltage will lead to very high losses in iron loss. So that factor will again increase your iron losses. So two factors are there to increase iron loss, one factor is there to reduce iron loss. So it will require very deep analysis, right? It is not very straightforward. You will require finite element analysis software to identify the losses. So that's why I guess most of the times examiners do not concern with iron losses.
Yes,
Did you
sir.
get this point? Why
Yes, sir. Yes, sir.
why yeah. Okay then. So yeah, it is very good discussion that and very good observation that you observed that yeah, because of voltage definitely iron loss should be considered. But anyway, that is the limitation with us, and that is very good thing also because we have very less time in exams. So you should not be concerned. If you further study or if you further pursue this area, then you will gain more expertise on that. For time being, I guess just focus on the examination.
Yes,
Okay,
sir.
sir.
Sure, sir.
Let's move ahead.
Yeah, getting it. So for such problems, what we do, we consider losses as equal. Okay, So what were the losses in two winding transformers? So for a two winding transformer, efficiency is provided, right? 96% of efficiency is provided here for two winding transformer at 0.9 power factor. So kVA is 15 kVA. So power would be 15 into 0.9. That will be the rated power. Okay, so output power is 15 kVA into 0.9, and that will be 13.5 kilowatt of output power. And losses efficiency is 96%. It means if you want to compute losses, you have to apply efficiency formula, output power divided by output plus losses. So 0.96 is equal to 13.5 divided by 13.5 plus losses. So how much losses will come out to be? $13.5 into 0.96 losses equal to 13.5. 1 minus 0.96 losses 0.04 into 13.5 divided by
Sir, 0.5625.
0.5625 kilowatt.
I have not considered the unit, sir.
Okay,
I just solved the equation,
Means
sir. 0.96 is equal to
so
13.
it should be 562.5 watts, because kilowatt it cannot be and watt it should be. So 0.562 watts also is not possible. So it is 562.5 watt losses. Each 562.5 watt of losses occurred at the rated condition of two winding transformer, right? Now for
Okay.
auto transformer, how much is the output power for auto transformer? I guess
165.
165 kVA with 0.9 power factor. So the output of auto transformer is 165 kVA into 0.9. So it should be 165.9, 148.5 kilowatt of output power of auto transformer. Now we have to compute the efficiency of auto transformer. So output is 148.5 divided by 148.5 plus losses. So losses is 0.5625, since every parameters we took in kilowatt. So kilowatt. If you compute it, you will get 148.5 divided by 148.5 plus 0.5625. It is 99.62. 99.62%. Okay. So you can see the difference between two equipments. When we used the same losses in two winding transformer, it came out to be, 96% of efficiency. With when we replaced it with auto transformer, we got efficiency as high as 99.62%. So efficiency is very much high compared to two winding transformer. So that one advantage you can visualize from numericals also. When you are solving such numericals, you should also, point out, or you should be aware that why it is happening. So I hope this question is fine. Any doubt, any final doubt with this problem, I will take. Otherwise, I will move on. So that conductive power transformer transfer and inductive power transfer in auto transformer, I hope you must have understood in yesterday's session. So as you told, I skipped those parts. So let us move ahead with this problem.
Sir, inductive power is nothing but rating of two winding transformer, right?
Yeah, rating of any winding. If you multiply 1500 into I1 or 150 into I2. So whatever winding is generating some kVA, that would be your inductive power. And the rest amount of power, if suppose 165 kVA is conductive kVA, and whatever the kVA you have generated through the winding V and I, the rest is transferred conductively. So it is similar to two winding transformer. Yeah. Or if you are given with the rating of two winding transformer, that same power, if that two winding transformer is reconfigured as an auto transformer, then the rating of two winding transformer, the same value will be transferred inductively in an auto transformer. Did you get that statement? So if let us suppose you have 15 kVA, right? You have 15
Sir.
kVA rating of two winding transformer, and you just directly want to compute the inductive power transformer transfer in an auto transformer. You can straight away say that 15 kVA rating of the power is getting transferred inductively. And here also you can see that I1 we have computed as 10 ampere, right? So 10 ampere, if you multiply with 1500 volt and 10 ampere, so how much you are getting? 15 kVA. So that much
Yes, sir.
kVA. Yeah. So that much will be your inductive transfer, and the remaining amount will be conductive transfer.
Sir, in this case, transformer ratio will change or not?
Transformer ratio has been changed. No, see here 1500 divided by 1650. Here 1500 divided by 150. So it will change.
Yes, sir. Yes, sir.
If it will be subtractive polarity, then it will be 1500 divided by 1500 minus 150, so 1350. So you have to conclude based on seeing this pattern. How is it additive? If it is additive, it means secondary side is higher than primary. If it is subtractive, it means secondary side is lower than primary. Then you have to conclude on yourself whether it is additive or subtractive.
Yes, sir.
But most of the
If this will be less, then we can also conclude that the transformer is stepping down transformer.
yeah, a step down. Yeah, a step down. Yeah. So till now, I have seen no question asked from subtractive polarity. There might be one or two, but very less question is asked from subtractive polarity in GATE exam also. So, but you should be well versed with all type of concepts when it comes to preparation. So maybe it is not a big deal. It's just subtractive transformer, and you just have to apply same principle. Just you have to mitigate the secondary voltage from the primary voltage, and you have to do the operation similar to what you are doing right.
Sir, in GATE exam, we are allowed to bring the calculator.
No, you will be provided with virtual calculator. So I seriously recommend that you stop using scientific calculator, whatever you are using, and you use virtual calculator every time. Even if you are computing now in session or anywhere, you use virtual calculator. But of course, in your semester exam, you will be required scientific calculator because you will not be provided with virtual calculator. So you just install that app of virtual calculator in your mobile phone, Android phone, or whatever, and even in your PC. It will be more productive if you are using virtual calculator in PC, because in exam your questions will be on PC and you have to calculate with the help of mouse, right? So you should be very well versed with the mouse operation on the virtual calculator.
Sir,
Okay.
if we will notice, that will be stranger for us.
Yeah. That will create very much. That will itself consume very much time, and if you don't know, because that operation is completely different from scientific calculator. So if you don't know, first
Sir,
you will start learning in the exam itself. So that we should always avoid.
sir, thank you, sir, for
Yeah, sure.
telling.
Welcome. Yeah. So should we move ahead with three winding auto transformer?
Yes, sir, sure.
Okay then. So read this problem. Uh, I will also read along with you. Okay, so here supply voltage is 700 volt, V1 is 400 volt, V2 is 300 volt. Load 1, here two loads are connected to two winding of different transformers of the same transformer, but two different windings of the transformer. So load 1 is consuming 800 kVA and load 2 consumes 400 kVA. Okay, so since Vs is given, V1 is also given. So what voltage will be appeared across load 1? Can anybody tell me this voltage?
Sir, 1100, 1100.
1100 volt. That's correct. 700 volt plus V1, right? So 1100 volt. Okay. So load 1 is having 1100 volt, and since load 1 consumes 800 kVA, so first thing what we can do, we can compute this current I1, right? So I1 will be 800 kVA divided by how much voltage? V1.
1100,
So
1100.
no, V1 400 volt, right? 800 kVA divided by 400 volt. Why 400, not 1100? Because this I1 is coming out of this dot, and this dot current will be generated if you have this V1 and this I1. That will be the kVA of that winding.
Sir, but the kVA of that winding is not given here, sir.
kVA of load 1. Okay, load 1 kVA is not given. Okay, that's correct. Load 1 kVA is not given. It means we have
Sir,
to take. Yeah,
sir,
yeah,
sir,
yeah,
sir, no, sir, the rating of the winding AB is not given, sir. Load 1 is
yeah.
given 800 kVA.
Yeah. Load kVA rating of AB winding is not given. So we have to take voltage of entire this A and D, right? So yeah, we will have to take 1100 volt because that current is going in load 1 and load 1 kVA is given, not the winding AB kVA is given. Hence we have to take 1100 volt. So it will come out
Yes,
to be
727.27.
727.27 amps. Okay, I1 we have computed now. We can compute I2, right, with winding CD because CD load kVA is
Yes,
given.
sir.
So
V2
I2
is
will
given.
be 400. Why this question discussed yesterday?
Yes, sir.
Oh, Okay, it means I'm repeating.
Sir,
Okay.
few students were absent yesterday. The other three, I think.
Okay, so I think you guys also getting revived and they will also be benefited. So 400 kVA divided by this V2. So V2 is given 300 volts. So it will come out to be 1333.33 amps. So we have computed I1, we have computed I2. Okay. So current is flowing in AB winding. If you are assuming all currents are flowing in this direction, then IAB, because enters a positive section AB, so IAB is nothing but minus I1, and that is 727.27 amps. ICD, this current will go in this direction, so ICD will again be negative. Why negative? Because we have taken this polarity of current, but ideally that current should be supplied to load, so that will be reversed. So ICD will be minus I2. So minus I2 means minus 1333.33 amps. Now we have to compute the current flowing in BC, and that BC winding will be having some current and some voltage. Both are unknown to us. So we will do that power balance or MMF balance. So we can take V1 into IAB plus VBC into IBC plus VCD into ICD. Or at the place of VCD, you could have used NCD or NBC, but again, if you replace that with voltage, so you will get at the end V1, VBC, VCD. Okay, so this is essentially MMF balance, or you can say power balance equation as well. So from this expression, V1 was 400 into 727.27, and that is minus plus ABC, IBC plus VCD is 300 into minus 1333.33 is equal to 0. And I guess VCD also, sorry, VBC also could be evaluated. So first let me write VBC, IBC is equal to 300 into 1333.33. So it is 30 plus 400 into 727.27. So 290,908. And VBC would be equal to 1100 minus 400 minus 300. Am I correct? Since 1100 is the overall voltage, and you reduce V1 and V2 from that, so you will get VBC as 4 plus 3, so 400 volt. So IBC would be divided in whole by 400 volt. So that value is equal to 987 amps. Okay.
Sir, we can directly calculate also.
Which one you can directly calculate?
IBC.
IBC you can directly calculate. How?
IBC is nothing but this primary current minus
Primary
this
current
I1.
Okay,
This
so
I1.
this primary current minus I1. Yeah, that is correct. And primary current we have computed. Primary current we can compute, right? VBC plus
12 1200 kVA divided by Vs.
yeah. That is also another way. Yeah, that is actually shortcut, I guess. So these are the ways you can compute. You just need to take care of proper voltage and current direction so that you can avoid all the mistakes. Okay. So coming to the final question, any doubt in this one? This problem, three winding transformer.
Sir, can you explain a little bit about this direction? I, IBC or ICD?
IBC or ICD. Okay. So see, uh, if you assume, let us suppose, let me remove first. Okay. Now this direction will be always there because of the load. It has to deliver to the load, so I1 will be always there. So if I am considering this direction of IAB, then it will be negative. Otherwise, you can consider this direction as well, opposite. Okay. Now this load 2 also must be catered from the CD winding and BC winding. So if you see uh, this current direction, this current direction will also must have this kind of polarity, but since you are considering this polarity, it is coming negative because before solving the problem, if you don't have any value, you don't know, but from the intuition you can see or you can guess that if load is connected, it means CD must be supplying to load 2. Okay. And whatever will be remaining, but regarding the BC, we must have doubt whether BC will supply to load 1 or load 2 or partially to both. So, and to which load it is supplying higher, to load 1 or load 2. So, at the end, if we have computed BC as positive, right? So, if BC is computed as positive, it means very less amount of kVA is required from BC to cater the load 1 than load 2. And it also implies that CD winding is uh, not not very much responsible for load 2 only, because BC is also catering load 2 in a huge way. So BC is supplying its most of the kVA to load 2 than load 1. So hence, when we computed the direction, BC direction is coming towards the load 2 rather than load 1. So that's another way to identify. Otherwise, at the end, if you are getting negative, it means whatever you assume, that is opposite of the reality. And if you are getting the same direction, it means whatever you assume, that is uh, supporting whatever assumption you have taken. Did you get it? Deepak, is it
Yes,
clear?
sir. I get it. Suppose one winding is delivering a current through the dot, then another two winding will take through the dot.
Yeah, if there is only one load, but here two loads are there. So it is, you can easily identify about CD and AB, but about BC, it is difficult to say just by observing. So for that, you need to compute and you need to see the load 2 is scattered by BC or not, or load 1 is scattered by BC. But here you can see that V1 is higher, like V1 current is higher. All the currents are, I1 is very high compared to, not very high, but it is enough capable to cater the load 1. because load 1 voltage is 1100, so it is very much capable to cater that load. But load 2, which is 400 kVA, and you see V2 and the winding current CD is very not very much enough capable to deliver to that load 2. So that kVA must come from some other winding, so it is coming from this.
Yes.
Okay then. So this is the problem where two different loads are connected with tapping of the transformer windings. So Z2 is given, Z3 is given as a resistive load. You have to compute the primary current I1 and also the power input from the primary side. Okay, so I guess it must be very easy for you, but just
Sir,
let me go
sir,
ahead
it is
and
simple to winding transformer.
yeah, it is just like two winding transformer, just that it is tapped from the secondary winding. So
Yes, sir.
okay, so can everybody solve it or should I solve it? Anyone? If one person will say that I need to solve it, I will solve it.
Yes, sir. We should solve because time is now remaining, I think.
Okay, then I should go ahead with the solution of this. So first
Sir,
thing
this
is
question we have not done yesterday.
okay, then it is good to discuss this problem. So whatever current will flow in secondary winding, okay. So let us assume this is the I2 direction and this is the I3 direction. So first thing is to compute I2. We can easily compute that because uh, Z2 is given and V2 we can easily compute. How to compute V2? V2 by Vs is equal to N2 by N1. Okay, so V2 will be equal to N2 by N1. So 400 divided by 1600 into Vs, which is 5 kV. So V2 will come out to be 5 kV divided by 4. So it is 1250 volt. And I2 then we can compute. I2 will be 1250 volt divided by Z2. So Z2 is 90 plus J60. So it will be in phasor, and if you compute 90 by J60, so 1250 divided by 90 plus 60 square, 1250 divided by 108.16 tan inverse minus whatever angle you will get for this impedance. If you are transferring it on the numerator side, it will come in minus, or this minus tan inverse 60 by 90. So I2 will be equal to 1250 divided by 108.6. So it will be 11.55 amps angle tan inverse 6 by 9. So 33.7 degrees. Okay, I hope everyone is able to do the phasor calculation because it is very important and very easy as well.
Sir,
Now,
in
huh,
in PC calculator we cannot solve directly this one.
in virtual calculator you are talking about?
Yes, sir. In virtual.
No, in virtual calculator you have to go with this step only. Whatever step I have written, first you have to compute the magnitude and then angle. And in scientific calculator you can compute at once. So that is the difference.
Okay. It means that it will be simple calculator, right?
Yeah, it will be just a bit advanced from the simple calculator, not exactly similar as simple calculator, but this angles and all you cannot compute in one operation. You cannot compute both magnitude as well as angle. So two different things you need to perform for this kind of operations. Okay, so first you need to compute the magnitude in that calculator, and then you need to compute angle separately. So that kind of operation you have to perform. Okay, so coming to I3. Okay, how to compute I3? So any guess how to compute I3?
Sir, we can calculate the rated current of the second winding, then subtract I2 from it.
Okay, rated current of second winding and then subtract I2 from that. Yeah, that is correct. But the rated current of second winding, okay, let us go ahead with it. So I2 rated. Uh, for that, you need to compute I1 rated. So how to compute I2 rated?
As
I2 rated
I,
we have already computed, right? So, and
so
the
I
current of
think
secondary winding is
Sir,
I3.
sir, we can calculate V3 by Z3.
Yeah, Z3 we can use. Yeah, that is also a way. I3. I3 is equal to V3 by Z3. Yeah,
Sir, they have given Z3 kVA, right? Because unity is power factor, so we can say 200 kV.
200 kVA. Yeah, that is great. So power factor is not given. Given? Okay, resistive load means unity power factor. So V3 first you need to compute. V3 is equal to Vs into N3 by N1. Okay, so Vs is 5 kV into N3 is N3, not only N3, we will require N3 plus N2. Am I right?
Sir, we have calculated already V2. We just calculate V3 and then added up V2 plus V3. This V3 is nothing but voltage across this N3.
Voltage across only N3. But if we are computing across Z3, so that voltage
Sir,
must
we
be
just
V2 plus
V2 plus V3. V2 plus
yeah,
V3.
yeah. So okay, so this will lead to 500 into N3 is 200 divided by N1 is 1600. So 500 divided by 8, sorry, 5000 divided by 8, so it is 625 volt. Is it correct? 625? 5000 divided by 8. 625 volt. So if you add V2 plus V3, it should be 1875 volt. Okay. And for this I3, we have to write V2 plus V3 divided by Z3. Am I correct? And Z3 is nothing but
Sir, just we will do 200 kV divided by this voltage
yes,
1875.
I3 into V3, and KVA3 is 200 is equal to V2 plus V3. So 1875 into I3.
I3 is 106.66 ampere.
10, could you please repeat? 1065.66.
6.106.
106.66. Okay, so I guess I3 should be correct. But in the question, it is asking primary current I1. Okay, so for primary current I1, we need to do the same transformation ratio. So N2 I2 is equal
MMF
to,
balance also yes.
so N2 I2 is N2 is 400 and I2 is 11.155, and there will be some angle minus 33.7 is equal to N1 is 1600 into I1. So I1 will be equal to 11.55 divided by 4. Is it correct? I don't think so.
Sir, I have got 40. Sir.
Sir, sir,
I1 should
sir, N1 I1 should be N2 I2 plus N3 I3, no?
that's what we did mistake. So in this whole N2 plus N3 into I3, N2 plus N3 plus, okay, just let me, we will see this circuit and we can write. So N1 I1 is the supply, okay, and N2 I2 is the one load that is getting supplied from the load, N2 I2, and other load is this Z3, and across Z3, this N2 plus N3 is the winding, this whole winding into I3. If you get confused in such kind of things, you see whatever the load is being supplied from the source. So source is Vs, right? So alongside Vs, we have only N1 I1, that is the MMF source. The load side is J2, so with J2 we have connected N2 and I2. So that is one MMF that is being supplied from N1 I1, and another load is Z3, so that is connected across N2 plus N3, and the current is I3. So with this approach, I don't think you will ever mistake. So if you now equate, you will get I3. So N1 I1 is 1600 into I1 we need to compute. N2 I2 400 into 11.55 angle minus 33.7 plus N2 plus N3. So N2 plus N3 is 600 into I3 is I3, where is it? I3, I guess 106.66. Okay, so by this way we can compute I1 will be equal to Now there will be one phasor operation. So first, let us compute this resistive component. So 600 into 106.66. So it is 63.996 ampere turns plus 400 into 11.55 is equal to 4620 angle minus 33.7 divided by 1600. Okay. So now if you perform, first let me, it is 2.8875 angle minus 33.7 plus 39.9975 angle 0. So if you add this,
43, around 43.
43 with some angle, right? 43, and what is the angle?
33.7.
33.7 cannot be, because 33.7 is attached to the first term and second term is real. So the real term parameter will change. However, imaginary term parameter will be same. So it should be less than 33.
Sir, in case of addition of two angle, what we will do here? We will add or subtract. Not add, not subtract. What will we do, sir?
We will add, see, but we cannot add a straightforward. You have two components, the real term, right? Real term plus imaginary term. So imaginary term will come out to be negative because cos of 33.7 is anyway positive, but sine of 33.7 minus is negative. So let me compute it for you. So sine, first cos of 33.7. So it is 0.83.
Sir, in
Uh,
in case of division, we we will subtract the angle to each other in case of division, and in case of multiplication, we will add the angle of these two quantity, and in case of addition, we cannot divide. No.
in case of addition, you have to perform addition by breaking the components in real and imaginary terms. You cannot straight away add the angles. In multiplication and in division, it holds true. You can reduce and you can add. But in case of addition or subtraction, you have to first break down all the components and then you can do. Otherwise, in scientific calculator, you can straightforward do the operation. But if you don't have scientific calculator, you have to break down all the angular terms, all the polar terms into real and imaginary, just like this. See, I have broken first term into real. Now I will break into imaginary. So that will be 2.8875 into minus sine of 33 point. So it will be minus 0.5548 plus the last term which was already in real only. So we can write it as it is. Now 0.832 into 2.8875, that is 2.4. So 2.4024 plus this plus this plus 39.9975. Okay, this is the whole real term plus imaginary term is in negative because it was minus. So
Sir, how you have calculated this 0.832 into 2.8875?
see 2.88375 you can see from here, right? Into cos 33.7. So cos 33.7 is nothing but 0.832.
Okay, it's okay.
you have, how will you break this angular term into cos 33.7 plus j into sine 33.7? So this is the
Okay,
j
means
into,
yes,
this is the
okay, sir.
imaginary term.
Means
Hmm.
uh-huh. Means sir, sine minus 33.7 is this minus point 548.
5548. Yes, yes, yes. So it will come
Okay.
out to be 1.6. So now you have to add this real separately and imaginary separately. So you will get 39.9975 plus 2.4024. So it is 42.4 minus j 1.6. Now you have to square under root and do that operation, and under root 42.4 square plus 1.6 square, and that you will get 42.43, and it will have some angle, right? And that angle will be negative because imaginary terms is negative, so negative tan inverse, or you can do tan inverse minus 1.6 divided by 42.4. So 1.6 divided by 42.4, so this angle will come out to be 2.16 degree. So this is very much less compared to 33.7. So you cannot write straightforwardly whatever you have in real component addition. So if you would have been asked this power factor angle, then you should calculate it in this manner. Okay, got it?
Sir, for solving this question, can we use the power balance equation, sir? The input power is equal to output power.
Yeah, because losses are not there, only load is there, so you can use that. And I would suggest you go ahead with that and solve and match the solution. That should actually match. If
Okay,
it
sir.
will not
Sir,
match, then we can discuss in next.
what is the correct solution for this question, sir?
A correct solution is that you balance the MMF and just like this. See, in the power balance, you may get confused at this expression. If you somehow able to manage by this expression, at the place of N, you can place V, that will be power balance. But if you are managed to write this expression just in like that, V1 into I1 is equal to V2 I2 plus V2 plus V3 I3. If you somehow arrive at this expression, then you are fine. Then you cannot do mistake. But there are high chance that you can do mistake at this step. Okay, or there may be low chance as well. That depends on you, how much
Okay, sir.
aptitude you have. So you must have arrived at this step very carefully, and then you are all fine.
Okay, sir.
Okay.
Sir, for this MMF balance, it is necessary to consider the, sir, phase angle, sir.
Yeah, if phases are there, if phase angles are there, it is very necessary. Otherwise, you will end up with some different value of current itself. You will not get 43 or 44 ampere, whatever you compute. 42.4, so you will never get. And power factor, you forget. Power factor angle, you can never achieve the exact. And in many exams, or even this exam also, exam of this course, you will be asked power factor angle, and you cannot do mistakes because this is very normal. This is time taking, but this is very easy type of problem. So you must carefully proceed step by step. Then only you can arrive at the perfect solution. So
Okay,
power
sir.
factor angle consideration or polar form of computation is very important for electrical machine concept.
Okay, sir.
Okay, then any final doubt before I wind up the session?
Sir, they did provide answer to you for this question.
Yeah, they provided, yes.
Sir, answer is coming same.
Answer is same, yes. Okay then, so I hope there are no further questions. Thank you very much for joining. Okay.
Sir, sir, you will upload it on NPTEL.
Yeah, I will upload on YouTube as well as if you will get on NPTEL as well. You have that access to Excel sheet, right?
Yes, sir.
Access.
Yeah. So if you don't have access, Deepak.
No, sir, we have access. I have
Ah,
access.
so if you have access, you can access it from the sheet as well. I will upload ASAP now today only. Within half an hour, you will get.
Sir, thank you, sir.
Okay, sir.
Okay.
Good night,
Thank you
sir.
very much. Good night. Good night, Neeraj. Good night, everyone. Thank you very much.
Good night.
Good night, Deepak.